Hello everybody and welcome to another day of CS 202, final week of the summer session. So, are we live? Things look different for some reason. Let me check. Yes, hello. Okay, cool. Alright, perfect. Well, today we are going to be talking about linked lists, and before that I want to do a little refresher on recursion because there's a few concepts that I didn't quite talk about last time with recursion, and I want to talk about it now before we move on. And yes, the theme song, too much effort to change it, so it's staying like that forever. It's free, no copyrights in it, so yeah. Okay. Why can't you see me actually? I just noticed that. There we go. Okay. Cool. Alright. So, with recursion, yep, there we go. With recursion, I listed a couple of things that I want to go over here in terms of 4 little topics that I want to mention and how recursion plays an effect with these. So, the first one is global variables, and so remember that when you do recursion, you got something in the form of a function that calls itself in what is known as the recursive case, and then you also have the base case, which is what stops the recursion from going forever, right? And so because of that, every time that you make a function call, it has its own copy of the local variables. So if you create any variables inside of the function, those variables are only going to exist in that specific function call. So if foo calls itself, because it's recursive, let's say that foo has a couple of parameters. It has a, b, and then it has some local variables x and y. Okay? So in this case, whenever foo gets called initially, and then of course we gotta make it recursive, so let's go ahead and do let's say it gets 5 and y gets 6. Okay? And so now whenever we call foo again, we can say foo is going to get called on a plus 3, and then maybe on b, and maybe one more line of code here. Let's say b gets y plus x plus b. Okay? Yeah, sure. I mean, this is kind of coming up as I go with it, but there's something that I want to point out about it. So, okay. So this is a recursive function. It's actually right now a infinite recursion because there's no base case. So actually, let's add one more line of code maybe. Maybe we go ahead and say something along the lines of if a is greater than 10, then just return. Okay, and there you go. Now we have a base case. Now, base cases don't have to be coveralls. Like, it must cover every possible situation. It must cover every possible logical situation where you would run into the recursion. So for example, if you think about 3 Fibonacci, the base cases was the 0th and then basically the first and second number of the Fibonacci sequence, right? 0 index and first index, if you think of it that way. And so it would make sense to have a negative Fibonacci number, so we don't even worry about the situation. But if for some reason we were to call the Fibonacci function that we made last time with a negative number, then our base cases would be useless and the thing would go forever in recursion. So that's something that you gotta figure out. If you want to do some kind of error checking to avoid that, you could add that as some sort of extra base case, but you don't have to, because at the same time, they shouldn't be calling on a negative number in the first place. And so with that some similar logic here, we have a function that has a base case, yes, but that base case is very limited and says if a is less than 10 return, which means that if a number is anywhere from 11 and on, then this thing will basically go recursive. And then if we have a number that is 10, or actually 10 would also go recursive. If we have a number that is like 9 or less, then it's not going to go into recursion. And so in this case, I mean, is there ever going to be a scenario where this function actually goes into recursion and it stops? And the answer is no, because this one is going only up. Like, the numbers are only going up and never down. And the way that we're trying to stop this is that it gets eventually smaller than a number. So really, while yes, this is a recursive function, it's never going to be the situation where this is actually going to be useful to us. So maybe we switch it around to make it something like that. So now we're, we have the same code in the sense of, like, we have a base case and we have a recursive case. It's just they kind of wrapped into one because there's no return key seen. But really, we just flip the logic now, because now if a is less than 10, you will keep going recursing. And then if a becomes 10 or greater, then you stop. So this makes a little bit more sense now, because you could start out with something like 1 in a, and then the next time it runs, a is going to have 4, and then plus 3 would be 7, and then plus 3 would be 10, and then that would stop at the 10, right? So a couple of things here. Every one of those function calls has its own x and y, and its own a and b technically. However, by saying its own, I mean their own copy of those variables or references to those variables in the case of b. And they all will contain their own data. Now, b is a little special though, because b is a reference, ampersand b up there is a reference. And because of that, it is not its own copy of the value b. It only has basically a pointer. And because of that, there's only one instance of it between all the multiple recursive calls. And so if I change something in one of the instances of the recursive call or recursive function, it's going to modify any subsequent recursive call and also ones that came before it once it eventually returns to those. So what I'm trying to get at here is that when you have multiple recursive calls, it's not trivial to pass information between each of them. And you're always assuming that you're running them in a sequential manner. There's no parallel or anything like that, because if you have parallel programming, you can't really do that because one of them depends on the previous one. So x and y, they have their own copies every function. So each of them could have the same data, different data, whatever, they're local variables. A as a parameter, there's also their own copy, and they could be different between each recursive call. For example, let's say we call foo from main, like I said, with something where a is equal to 1 and b is equal to maybe 1 as well. Okay, so we're going to call it like this. Obviously, we would actually type that like that, although actually no, this would have to be a variable. So, somewhere here we have like a variable b equal to 1 like that, because otherwise we can't call this on a literal, right? We talked about that with the L values and R values, because that's being passed by reference. And if you pass a literal by reference, you can do it, but you have to put const in front. Because if you don't, what's going to end up happening is, if you try to modify it, you're modifying somewhere in memory you shouldn't, and the whole thing will break. So you can't do that, right? So anyways, we pass another variable here. And so now dog is barking. And so now, basically, this function gets called, things happen here, and eventually it gets called again with foo having 4, comma, and whatever is in B. What's in B? It's going to be 1 plus 5 plus 6. So that is going to be 12. And then that has its own copy of variables once that function gets created. And so that has its own x, its own y, and then the a and b are their own parameters, which has 4 and 12. And then the next time it gets called, once it runs to the code again, because still 4 is less than 10, then you're going to have 7, comma, and then 12 plus 11, essentially. 12 plus 11 is going to be 23. And so that's going to be another call. And that's going to have its own x, y as well. I know the x, y's are going to be identical, right? They're all going to have 5 and 6 because we don't really modify x and y. We just declare them. But that's okay, just for sake of the example. And so the next time around, the 7 is still less than 10. So you do go into the if statement. And so you do another recursive call with foo being 10, comma, and then 23 plus 11, which is going to be 32. Oh, no. Wait. I hope I didn't do the math earlier wrong. 12 plus 11 is, 12 plus 11 was 23. But then this should be 34. And so this gets called again. And then this time around, however, you actually never make these variables x and y because you don't get to that line of code. Because what happens is, when you go to the top here, you say if a is less than 10, that's false. Because a is equal to 10. So you don't even enter the if statement, you get to the end of the function, and then you're done. So then you go back to the function over here, and then you finish the code. Now, right now, we don't have any code beneath the recursion, but it is very possible that you could have code beneath a recursive call. You could even have another recursive call, like we did with the Fibonacci. And so that brings us into the concept of doing things before and after our recursive calls. And that is what is known as head and tail recursion. So in head recursion, typically the first thing you do, and these are just names really, is if you have something like a function, so we're going to call this b, you do whatever you do in b, you do your recursion initially, and then you do other operations that are non-recursive. That is what's known as head recursion. Tail recursion, on the other hand, in fact, instead of calling this b, we'll call it h, so you can remember that. Tail recursion, on the other hand, typically involves doing operations first, and then going ahead and doing your recursive call. However, in either of these scenarios, you still need to have your base case up here, even within head recursion. And the reason for that is because if you don't have your base case code before the recursive call, then they will go forever. Now, in the case of tail recursion, it doesn't have to be at the top. It could actually be right before the recursive call, but it has to be somewhere in here. Whereas here, it has to be the only thing before the recursive call because it's head recursion. Okay, so I'm not trying to say like one is better than another one or anything about which scenario you use each of them, because they come in useful for different things, and typically you should be able to convert things between head and tail recursion in a rather systematic way. But they will talk about that more when you get to like 326 and stuff like that for parsing and those sort of typical things, like when you're talking about like expressions, regular expressions and things like that. So there's different approaches to solving problems, basically. Typically, tail recursion is sometimes a little bit easier to wrap your head around. And for that, actually, let's talk about the next thing here. I wanted to talk about statics, but I'll come back to that one. Let's talk about list and how to print out a list recursively. Okay, and you might have done that in your assignment already, I'm not sure. But either way, I want to bring it up here. And so suppose that we have an array. size. It doesn't really matter the size, but we have some sort of array here, okay? And then it's initialized with some data. And so my question to you is, how would you, if I asked you to print out the contents of this array, how would you do it? And you would more than likely, if you're writing a function for this, call it print or whatever, you would pass in the size and the array as the parameters. So let's say this is an array of integers. So then you would say something like int r and then int s for the size. Okay? And so inside of the function, you would probably write a for loop or a while loop and then basically just print it out and then call it a day, right? Let's go ahead and actually do this using a while loop instead of a for loop, okay? So we would say something like while, and then we need to have some sort of counter since we're doing this kind of by hand. So we'll call that counter I, and we gotta initialize that counter to something. So we're gonna initialize it to the beginning of the list, which is always 0. And so, or at least that's a claim we're making. And so we would say something like while I is less than the size, which is s, then you can basically say cout r sub I, maybe end line after that. Okay, and that's it. That would basically make sure that, oh, well, we need actually one more line of code, I++, okay, because that thing needs to be able to go to the next thing. Otherwise, you're looping forever on the first spot. Okay. So now, if you were to write this recursively, how would you do it? Well, right now, if you kind of visualize the list, you're keeping a pointer, although don't confuse that with pointer in C++. I mean more of like an index, but you're keeping a pointer to a location in the list, which is where you're looking at. And then you print that out, and then you move it on to the next spot, and then so on, and so on, and so on, and so on, right? Okay, when you're doing this recursively, you want to think of the list as made up of two parts, where you're at and what's left. And so the first time around, those things are actually basically the same, basically kind of like the same thing, because you're basically at the beginning and you have the rest of the list to print out. But the next time you do the recursion, you're actually going to look at the remainder of the list here and then call the recursion on that, but printing out the next item, so that way you move on like this. So in a way, if I copy paste this real fast, the next time you do the recursion, it would actually be like if you were looking at, change colors. Oh, come on. It would be like something like this. So you're looking at the next item in the list, and then you're sending over the remainder of the list to the next recursive call. And so the next time you run this, again, you would basically send the remainder of the list to look at the next item. So you would look at that one. And so on. And so this is what sort of that divide and conquer in a way. And also you're slowly making the problem smaller by chipping at it away. And so the recursive code to basically do this this a little bit down so we have space, will be something among these lines. We'll call this print recursive. We still need a pointer to the array, and we still need to keep track of the size. However, you don't need to do anything fancy like you did here with the counter, because what we can do is we can use pointer arithmetic to keep track of the counter within the parameter. So you could do something like cout r dereference, and that would always print out spot 0 if you remember your pointer arithmetics. And then we can also add in our base case, which is basically okay, all right, I will show you two versions, but let's make first easy version here. Let's go ahead and actually have, so this will work what I was going to do, but I don't want to confuse you yet by doing the tricky version. Okay, so let's add one more parameter right now, and then we'll come back and think about how we can do this with these two parameters. Okay, so let's add one more parameter, which is going to be where we're currently at. Okay, we'll call that one char for current, or actually we'll call it I, since that's kind of what we did above. Okay, so now in this scenario here, that makes it even easier, because we can either look at it in terms of pointer arithmetic, or we can just put the I inside the square bracket. So let's go ahead and do that for this version, and then we'll come back to the pointer arithmetic, as I said. So if we're doing that, our base case is going to essentially be to say if I is less than S. Okay, because if it's equal to S or greater than S, then we don't want it to go and print out anything. We just want it to stop, right? So again, you know, we could write this by saying if I is greater than or equal to S, return, but you know, you don't always see that when you're writing your recursion, and so, you know, we'll write it like you normally see it. Okay, and then the only other thing here required is to do the recursive call. So we're going to call print rec on R, and then S, which is the same. And the only one that is going to change here is actually I. It's going to be plus plus I. Not I plus plus, because in that case we will never advance. We will just be printing the same thing forever. Because remember that the post increment basically gets the old value and then increments the local variable. But that local variable is only local to this specific recursive call. So the next time around it's going to have the old value, so you'll never get anywhere. So by doing pre-increment, you actually increment it and then pass it in as a parameter. So that's okay. So this would essentially do the printing. Okay. Now, can we basically do this in just two parameters? And the answer is yes, it's possible to do. And that's kind of what I was going to do, but then I was like, maybe show the easy version first and then go to the sort of trickier version. So let's go ahead and try to do this again, but this time we are going to we're gonna try something kind of cool here. Okay, we're gonna sort of print it backwards. Okay, so we're gonna get rid of one of the parameters here, which is I, And also, we're going to do this with pointer arithmetic because it's cooler. And we know that S is the size, right? So it's going to start out at the biggest number possible. And rather than trying to, because it's passed by value, you know, we don't risk modifying the size variable in main. So what we can do is we can actually use the size to print out the last item and then count down all the way to 0 because we know that the beginning of the array is at 0, and that is when we can actually stop. And so we could say something like cout AR plus the shift of the size. So, you know, we could do something like cout AR plus S, which could also be written as ARS, by the way. But again, nice practice of pointer arithmetics. And then we can just go ahead and decrease S. In fact, if we want to be really hardcore, we could do it in the same line. We could just go ahead and do it here by saying S minus minus, but you know, we're not going to be that crazy. We'll put it here, S minus minus. And then we need to have a way of stopping it. So again, we could say something like if S is less than 0, we could say return like that. Or better yet, we can simply say if S is greater than 0, and then just have our code like that. Okay? And so now we just need to modify this. Okay, so for this, we can say AR and then S. In fact, actually here, let's just go ahead and do the S minus minus and the recursive call. Minus minus S. However, the way that I have this right now, it's printing things backwards because it's starting out at 10, which is the biggest number, and then it's going to print out 9, and then 8, and then 7, and then eventually it's going to get to 0, and then it's going to stop. It's actually going to have one extra recursive call when you get to 0, because you know, when this is when S is equal to 1, it's going to go here. It's actually going to print out the spot 1, index 1, and then it's going to go to 0. And actually, technically, we're not going to print out spot 0 as it is now. I guess we got to make this equal to 0 here. Is greater than or equal to 0. There we go. Okay, so now it's going to get to spot 0, print out spot 0 as it should, and then it's going to make one extra recursive call to spot -1. That will then not go in the if statement and come out of that. So yes. Okay. So this is cool because we save one variable, but it's backwards, right? You know, it's backwards right now because we are printing sort of in a countdown manner. Okay. Can we basically flip this around to print out forward instead of backwards? And the answer is yes. We can just convert this from tail recursion into head recursion. And that just basically means flip these two lines like that. So basically you take the cout line and put it like that. And so now we flipped it from what would have been tail recursion into head recursion. What's going to happen now is you're going to have, before you print out anything, you're going to have like 10 of these recursive calls. It's going to go all the way until 0 because it's going to go S, and then, you know, S is going to start at 10. Oh, S is going to start at 10, and then it's going to go into the recursive call, and then 9, and then 8, and then 7, 6, 5, 4, 3, 2, 1, 0. And then the 0th call, when S is equal to 0, it's going to go in here one more time into -1, and then there it's going to come back. And once it's come back, you know, as it's sort of unwinding the recursion, because you could think of this as like, this calls this, which calls this, which calls this, and this is like 4, 3, 2, 1, 0, -1. The -1 doesn't do any printing, but when you come back to the 0, you just came back from here, and then you're going to do the line beneath it, which is a cout. So now you're going to print out the 0th element, and then that's going to finish, and then you're going to go back to 1, and you're going to print out the 1, and because that's the last line, the line of code after the recursive call, and then the 2, then the 3, then the 4, then the 5. So as you're unwinding the recursion on your way out, you're going to be printing the numbers. And so now we fixed the issue with it being backwards, but still maintained only 2 variables in there. So yes, this might be easier conceptually, but this is also important to understand that it's good, not just because we save a variable, because there are different ways of approaching it. Here, as we're going into the recursion, we are basically printing as we go in. And then when we come back out and unwind, it's just like unwind, 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 unwind. This one, because it's head recursion, we don't do any printing on the way in. We do it on the way out. Okay, so there's code after we come back from a recursive call. And so that's another way of doing recursion for different tasks, such as, for example, printing a list backwards, or a list that is backwards, printing it forward. So hopefully this is, making sense. And so there's one more thing about this that I wanted to point out. And that is, if you look at the recursive call and the iterative call, they're very, very familiar, or they're very, very similar. Okay? It turns out that for some baby or basic examples, there's a very easy way to convert iterative code into recursive code and vice versa. Although any recursive code can be converted into iterative code as long as you have one data structure associated with the code, and that's a stack. We haven't talked about stacks yet. Hopefully we have a little bit of time to talk about them on Wednesday. But a stack data structure is basically also how memory works. And because we can mimic that using a stack, we can convert any recursive code into iterative code by just converting it into a loop and using a stack. On the other hand, we can convert any iterative code, any code with a loop, very easily into recursive code, as long as we can potentially use a stack as well. Or in that case, actually, we might have to use like static variables or global variables. Global variables probably not, but statics potentially. But what I'm trying to tell you is that any code can be converted from recursive to iterative and from iterative to recursive. It might make the code harder and more complicated, but it's definitely possible to do. So it might be a good thing to prototype something in a recursive manner, but when it comes time to actually implement it in the real world, you may find yourself better off converting it into iterative code. And so, well, sort of the process of doing that with complicated things is kind of like beyond the scope of this course. I do want to show you a basic example of converting iterative code into recursive code. And the print function here kind of works out for that pretty well. So we have our print function here, and I'm going to modify it a little bit. You might be like, I'm actually making it worse in a way, but that's only because it'll make it easier for you to see it, visualize it, how this will become recursive code. First of all, you might be asking yourself really why I use the while loop, and this is the reason why. What I'm going to do is I want to make that loop infinite, and I want to bring out the condition from the while loop into an if statement using a break clause. And so I'm going to go ahead and bring this down and then take this out, put it at the beginning of the loop, because otherwise I convert a while loop into a do while loop, which is a bad thing because it changes the logic. And I have to flip the logic of the conditional. So like from I is less than s, I have to now flip that to say if I is greater than or equal to s. And then I can put the word break. And that is basically the same thing. If I put this here as having my condition inside of here. But now I'm just going to put it true. And if you don't believe me about that, go ahead and try it out in code. Now, the code is still doing the same thing. However, even though the code is doing the same thing, this code is very easy to see how it would look like recursively. And I mean, we already saw it, but this itself, as it is now, pretty much looks already as recursive code. Because all you gotta do to convert this into recursion at this point is you basically separated a base case, which is your break, and then if you wanna feel better about it, you can even write the word continue here. But again, it's at the bottom, so it doesn't matter. But essentially, if you want to make this into recursion, as you have it now, all you have to do is turn the while loop into the actual into the recursive function. So basically, get rid of this, and then leave this in there. And then bam, you have basically created recursive code. You just have to change the word break for a return, and then add in your recursive call at the bottom where you would have put a continue, which would be here. So basically print R, because you still need to have the array, and then you can, the second parameter you see is this I, right? So that I was initialized beforehand. You don't need to do that initialization in the recursion because you assume that that initialization is going to be done in whoever calls you the first time around. So you have two options for that. You can either move that parameter or any other parameters that are supposed to be updated into the recursion up here, like this, or without the pluses. That's one option, and then you can just go ahead and put, plus plus I like that. So option one is like this, and at this point you're pretty much done with this. Alternatively, in fact, here, this one down there. Alternatively, what you can do is you can use a static. Well, here, let's go the easy way first, the bad but easy way. We could use a global variable, right? And I is equal to 0. Now, if we use a global variable, oh, and I suppose I never added the s, but also add the s in there. There we go. Okay. So if we use a global variable, it actually makes things easier because we can still keep the I++. So this almost looks like the iterative. In fact, this looks very, very much identical to the iterative version of this. Like we have the I++, we have the cout, we have the if statement. Literally the only difference between these is that the I equals to 0 is outside the function. And then also, and then basically the recursive call, which again, if you want to have an equivalent line in iterative code, just write the word continue at the bottom. Okay, like that. And then bam. Now it looks pretty much identical. However, global variables are very bad. And one of the easiest ways to catch someone who has no idea what they're doing is they're trying to use recursion using global variables because they can't think because of well, that sounds bad. They can't think. Let me finish the sentence. They can't think of a way of passing in data between different recursive calls with parameters. So anything that you could potentially have that makes your life easy by having a global variable, you could just have as a parameter, and you could pass in by reference or by value, however you want. But you can have it as a parameter. So like how I have the parameter there inside and then just pass it in here is a much more elegant and better way overall than it is to just have a global variable outside. In general, global variables are just bad because they are potentially variables that are going to be there for every other programmer. So I mean, I guess semi-bad would be that it's a class variable. So it's still a bad way of doing it, but at least you're only affecting your own code and not other people's. So no, don't do that. Again, the best case scenario is just to do the parameters, but another way to do it that is better than the global, but still not as good as doing the parameter, but I guess it would be more acceptable per se, would be to use a static. So remember statics, hopefully you do, and if not, then revisit the videos. But with a static variable, remember that there's only one instance of them in a class, for example. With a class variable, there's only one of them no matter how many objects you have. And for a function, there's only one of them no matter how many function calls you have. They all share the same value. In fact, what's kept inside the static variable is a reference to somewhere in memory. And so it's kind of like a global variable in a way, but it only exists and is only accessible inside of the function. And so in this case, the way you declare that is you basically add the modifier static here. So, and because statics cannot be initialized multiple times, whatever you put as the initialization there is just going to happen one time, and that's it. I think it's like this. You might have to put the word static before int. I'm not 100% sure because I don't really use that statics like that. But I think it's int static I equals 0. It might be static int I equals 0, okay? You guys on chat, let me know. But yeah, and this actually looks super like even closer now to the iterative version actually. I mean, aside from the word static being in there, they're pretty much the same. So it is static int I equals 0. Okay, thank you. So there we go. Like that. And so now, every time you call this function, it's going to have an I, yes. But that I is not going to be initialized every single time to 0. It's only the first time that it gets called. In fact, the initialization happens even if you don't call the function, technically. So this line of code is just run before even the function gets called. But you can access that I inside and you can modify it, and it's only going to modify the one instance of it. So a good usage of statics and functions like this is to keep track of how many times a function has been called. But otherwise, you'd have to have a parameter and then keep track of that in main or something. So there are usages of static and functions, but you know, using them for recursion is probably poor practice because again, there are better ways, but you're just not familiar with them, and you know, it's like using globals in a way, but not as bad. Okay. So that's kind of the usage of static with recursion. And finally, I think I have one more thing. Oh no, I did already. Iterative to recursive code. The same can be applied if we had some sort of recursive code. So maybe let's see if we have some recursive code here. With the Fibonacci, you definitely need to have a stack when you when you turn this into iterative code. So don't want to go. Maybe we'll go over that when we talk about stacks. But at least you kind of got the idea of converting iterative into recursive code. Okay. So that's it. That's all I wanted to talk about recursion now. These are just tiny little extra things to get to Thursday's lecture. Okay. Are there any questions on recursion before I move on to linked lists? Let me know on the chat. Drink water in the meantime. Okay, so while you guys decide if you have questions, let me open up. I think on Canvas I have some really nice pictures about linked lists. Oh, I have a recursive main. That sounds cool. Can you explain the difference between head and tail recursion again? Head and tail recursion is going to be when you do the recursive call in your function. if you're doing it at the top of the function, obviously you always have to have a base case before any recursive calls. Otherwise, the thing will go forever in infinite recursion. So once you do the base case check, you're probably doing something in the function, and then you're doing the recursive call. The example of that is when we were printing out in the array, right? We have this print rec, and in this case, we have our base case, which is the first line of code there in a way. Then we have the recursive call, and then we have something that the function is actually doing, which in this case is couting. In this case, we're doing the recursion before we do the printing. Because we're doing the recursion before we do the printing, and the printing I want you to consider the job of the function. So we're recursing before we're doing the job. In this case, it's head recursion because we are doing the recursion before the job. In the other way, in here we have the base case check, and then we're doing the job, which is printing, and then doing the recursion. Because here we're doing the job first, this is tail recursion, because the last thing you're doing in this function is doing the recursion. Whereas here, I would say it's almost the first thing that you're doing after the base case check. So that's the explanation again between head and tail. So now I'd like to turn your attention over to Canvas for a kind of neat thing I forgot I had in Canvas that I wrote, which is called a recursive main. So you can call main. Main is of course where the functions, when C++ functions start, right? You know, everything starts at main and ends at main. That's the last thing that runs, right? So the question was, I guess at the time, can you have a recursive main? And it turns out that you can, and it's pretty cool. Obviously, the first time main gets called, it actually gets called by, I suppose, when you load the code into the computer and it executes, it's just where it starts running the code, I guess. And so, you know, we are couting. We have two parameters in main always. Those parameters are your argc and argv. However, nobody states that they have to be argc and argv. That happens the first time because that's something that is passed by the OS. But if I'm going to call main again, then they can be my own variables at that point. So, you know, I call them, you're not limited again in C++ by the name you have to give them. So I call them N and C instead of argv and argc and argv. Of course, the first time you call it, N is going to have potentially a 1 if there are no extra arguments, and it's just the executable name. And then car C is going to have just the file name, I suppose. But they could have different numbers in there, depending on the number of arguments you have. And so the next thing you see here is I'm declaring a variable x equal to 0, and then I'm printing out x. So I guess it's just printing out always 0. And then if x is equal to 5, return 0. Should that be n? I feel like that's going to go forever like that. Oh, no, I'm reading it in. Sorry, not couting, c-inning. Okay, so I'm reading it in. Yeah, okay. So I'm reading in some value in, and then it's so that I can recurse as many times as I want until I stop it by hand. Yes, okay. But if the number I enter is 5, then I can stop the recursion. And if I enter some other number, then I am going to basically call main again. So see, this is where I'm calling main, because main is just a function, just like any other function, and anybody can call it, including yourself. And I'm going to call it on n plus 1, n being, again, the size, the number of arguments, plus 1, and then c, I'm passing in c again just because I can. And this would actually call main again, and so now you could have some sort of recursive main, which is kind of cool. So not much real application on this other than it being kind of cool because we think of main as this sort of special function. It's not. It's just like any other function. The only thing is that makes it, I guess, different is that our programs start there in C++, but and they end there. But what we do with it, you know, we can interpret it like any other function. In fact, when you're doing like multi-threading and threads in general, you find that you have to have main do different things depending on if the thread is a master thread or a slave thread. So, yes, that's That's just an example of main being called by different things and doing different things. Being called with different purposes, I suppose. Better way of saying that. So yes. Okay. So now linked lists. So I have a bunch of examples of linked list code. But I want to start out by defining a linked list. And before I show you even that, actually, let me propose to you the reason why they exist. So I know you know vectors, and they're great, and they are. You know, let's forget about them for a minute, though. I think my internet just disconnected. I am seeing very low upload. Are you guys still there? Or should I wait a minute? The bitrate went down to 0. Okay, now it's coming back up. So if you guys are still there, let me know. Because I think we had like a hiccup on the connection for about 5 seconds. Still here. Okay. Yeah. It basically, I saw it cut off for like maybe 3-4 seconds here on the upload. I had the kilobits per second upload, which is around 6,000, and it dropped down to like 50, and then 0, and then like 100, and it was just like that. But okay, I think we're back. Cool. So refresh if so that there's no, because I added a delay. So refresh. But okay. So arrays are cool, but the biggest limitation of the array is that you can't insert things in the middle of an array, right? And also, I guess, along with that limitation is, in general, inserting things into the array is just not possible. That might be misleading to say, because you can change things in your list, and if it's not full the array, you can, I suppose, quote unquote insert, but you're not really inserting. You're just replacing things that you had marked as empty, right? Because an array is a fixed size, and once you declare that array, you can't change the size ever. You can make another array and then copy the contents over to the bigger array, and then delete the other one, and then you could even use pointer magic so that they're called the same, so they're both called R. So you can do that. You can declare an array of size 10, if dynamically with an R pointer, and then if that's too small, you can make another array called R2, make that size 15. Do a deep copy by copying everything over, then delete the old array, and then update the pointer to point to R2, so R still points to R2. So you might hide from the user the fact that you completely made an entirely new array and copy things over. They might still see it as R, but you know the truth, that it's a completely different array, right? And so that's the limitation of arrays, even dynamically allocated arrays, that they are fixed size, and if you want to have more space, you have to copy everything over into a new one. And furthermore, for any kind of array, you can't just insert something in the middle, because what do you have to do in that case? Well, you'd have to make an array of size +1 bigger, so copy everything into the new array, and when you're copying over, you copy the first part of the array the same, because you haven't done anything to that, but then the remainder of the stuff you have to shift by 1, so that you can have space for the thing you're trying to insert in the middle here. And if you do that, you're great, for now, until you have to insert something else, and then the process repeats itself. Similarly, suppose that we want to delete this here. Well, there's no easy way to delete things. I mean, you have to basically shift things around, this part here, whatever's here, you have to shift it here, and then you have a sort of an empty spot in the array. So if you want to make things quote unquote clean, you have to copy into a brand new array of size, let's say n-1, and being the size of the previous array, and then the first part of it gets copied the same here, but then the remainder of it has to be shifted by 1, so that we cover the spot that we just removed, right? So it's a complicated process, and that's actually what vectors are doing. When vectors are allocating memory, copying things behind the scenes and all of that. But there's a lot of copying going on, and it's very inefficient, okay? It's very, very inefficient. now that we know pointers, we ask ourselves, how can we use our knowledge in C++ of pointers and things like that to solve this issue of being limited by inserting and deleting in the middle and growing an array? Is there a way that we can circumvent these problems and come up with a better way of storing information? At least better in some ways, but as we will see, there are pros and cons to everything, right? And so this is how linked lists were born. So that's going to be the next topic of the day, linked lists. As the name implies, they are lists that are linked, and those links happen to be pointers. And so a linked list is a dynamic list of items, and these items, which are the data, are contained inside of what we call nodes. And the order of these nodes are determined by the address that we call the link. So let's go ahead and draw this out. Think of it like a chain, okay? And yeah, chain could work. After all, they are linked. So a node is typically made up of two things: data and the link component. The data component is what you're storing in it. So if you have an array of integers and you want to make a linked list of integers, your data is going to be an integer. Could be an object as well. Could be other linked lists as well. Could be anything. The link component is a connection to another node, like that. And that other link component could be a connection to another node. And as you can see now, we're starting to create this sort of chain that is linked together. The cool thing about this is that they don't have to be stored in the same spot in memory. I could have each of these links stored in completely different locations in main memory. So I can do something like this technically. So in my main memory, I could have one of the nodes here. So each of these are called nodes. So I could have one node there, another one here, another one here, another one here. And the way that I have them linked is maybe this one goes here, then this one goes here, and then that one goes there. And maybe from there we go there, and then from there maybe we go there, and that's the end of the link. So that's kind of the end of it. I like to draw this symbol to represent the end of the link. However, because the links of the linked list are pointers, what do you guys think is going to be in the last link to signify that that's the end of the linked list? We have two options there, I suppose. No, yes, you're right. So this is indeed going to be basically null. So the last item of the list, the last node of the list, is going to have a null to signify that it's the end of the list. You might think like, oh, it might be nice to set that link to be pointing to the first thing so that we make a sort of a circle. I suppose that's a valid idea if you want to make a circular linked list. However, problem of doing that is, how do you know where it ends? Because it technically doesn't, so it causes issues if you do that. So yes, null is the best choice at this point, okay? So we have a linked list. It's made up of nodes. These nodes have the data and a link component. Eventually, when we talk about a double linked list, you will see that they have two links, but we're not there yet. And then also know that that you set the link to null when you reach the end of the list. Okay. Now these nodes are dynamically allocated. That way you can add as many as you want. And here's the thing. Suppose that this is my current list and I wish to add another item into this list. I go ahead and create a new node. Bam, I just created a new node. fill the data with whatever I need to store, set the link to null initially. And so now my question is, where do I want to put this data? Well, let's say we want to put it at the beginning. If we want to put it at the beginning, that's very easy. Let me just shrink it a little bit. I'm going to put it right there because that's the beginning. So now, I suppose this does bring up a question. How do we keep track of the beginning of the list? Well, it's very useful to have a pointer of the type of whatever link is, which is, so in this case, probably an integer, that we typically call head. And head will point to null if the list is empty. Otherwise, it will point to the beginning of the list. So in this case, let's say it's pointing right here to this node. But if we go ahead and then insert the one we just did, then we can update this pointer to point here. And so now, if we wish to traverse a linked list, which means to be able to walk through it and maybe print the data or do something to the data, then what we do is we just dereference the head and then go there, which takes us basically right here, and then take the link to go here, and then link, link, link until we get to the null at the end. Okay? So this is great. All right, what do we want to insert a node at the end of the list? Well, we first declare our node as it has been allocated, and then we can just go ahead and update the last pointer that's here so that this is no longer pointing to null, and instead it's pointing to our new node, and then make sure that this one is pointing to null to signify that it's the end of the list. So we can insert in the beginning and we can insert in the end. Can we insert in the middle? Yes, we can. Let's say we want to insert between this guy and this guy. Okay, no problem at all. Step one, allocate the new node you want. So like declare, with that dynamically allocated like that. And then go ahead and switch the pointers around. So now let's go ahead and copy this pointer here. Let's take that pointer and point it right there. And then instead of having this point to null, let's go ahead and point it right there. And so now we basically inserted it in the middle. And here's the cool thing about all of this. It doesn't require any resizing, deleting, or copying around. All we had to do was allocate it and then just move a couple of pointers to update how this thing is linked out together. That's very fast. It's much more efficient. Furthermore, we can keep adding links to this linked list until we run out of memory. And so it can grow, it can shrink, I can insert, I can delete, and those operations are very, very fast and much better than arrays. So you might be thinking, wow, this is amazing. Why do I ever want to use an array? Because there's a catch. With arrays, you can access any position of the array at any time. All you have to do is basically get the index of that position. So if I want to access the fifth element of my array, we use the array index operator, and we put in, technically I suppose the fifth element will be at spot 4. That, because array start at 0. But yeah, you can access that immediately. This gets converted into pointer arithmetics, right? So you get AR plus 4, like that. This works because at least to the computer or to the program, virtual memory paging aside, 219 land, it's kept as one contiguous block of memory. And so if this is the beginning of the array, we can do plus 4, which is the size of the bytes. So this probably is 4 times 4 is 16 bytes down to find actually wherever the plus 4. Yeah, that shift. So so somewhere in there will be store days, but the point is that because we can just do the pointer arithmetics, we can immediately go there. We can just go directly there. We don't have to look at any data before. We can jump right in. That's the advantage of arrays that we don't have with the linked list. With the linked list, Look at how it's stored in memory. It's all over the place in memory. There's no easy way if we're here to be able to go here. The only way that we can traverse this linked list is by going through each of the links and sort of following the roadmap. So for example, where's the start of this? I guess the head is probably here. The head itself is a pointer too, by the way. So let's just say that that's the head actually. And then the head is pointing to the first thing, which is that. So suppose that I wish to access this right here. The only way that I can do that is by going into the head, which would be, I'll highlight and then erase it right here. Come on. And then taking that pointer to the next thing. That's not what I want. Keep going. Keep going. And then bam, finally I got there. I had to go through all of that path to be able to get to that spot, the blue square at the bottom. There isn't, and you might be thinking, well, can't you just see us at the bottom? No, I can't, because these are kept in memory in who knows what order. And I can't keep track of that because they're just pointers. And so I have to dereference the pointers to find out where the next pointer is. It's almost like going in a scavenger hunt where like each place you go, it gives you a clue to the next spot. You can't skip ahead. You got to go to the clue, get that clue, figure out where the next spot is, and then go there to get the next clue. There's no easy way to just get the clue to the end because nobody knows. Each node only knows what it's connected to, like the immediate person is connected to. It doesn't know what's two spots ahead. It doesn't even know if it exists or not. It just knows that, like, look, the next place you gotta go is like Alabama or something. All right, I don't know what you gotta do after that. That could be the final node or not. It knows if it's the last node because it's it sets to null. But if it's not, then it doesn't know anything. Okay, so it's like you're hunting for treasure here. Okay, and so because of that, in the worst case scenario, what you're looking for would be the last item in the node, or sorry, the last item in the list, and so that is going to be very slow. Yeah, essentially, like, where's the toilet, and they just kind of point that way or something. So yes, and so because of that, accessing data or searching data on a linked list is far slower than an array. And so while I am going to talk to you about linked lists, and I'll show you some code and all these things right now in 202, you will revisit linked lists when you get to 302, and you will look more at that analysis of how they're slower when you know about big O notation and time and space complexity. So you will come back and they'll talk more in detail about this, but I think you can already sort of figure out why they're slower based on what I'm telling you with the dereferencing, right? It makes sense. But basically, searching through a linked list is O of n, whereas an array is a constant. Accessing a member in a linked list can potentially be O of n, whereas accessing anything on an array, an index, would just be constant time. Searching through a linked list, when it comes to an array, you can use binary search to search through an array that is sorted in log n time, versus a linear search would take you n time. With a linked list, you can't do binary search. You are stuck to using linear search, which takes you n time. So while you can search something in log n time with arrays, if it's sorted nicely, you can't do that with a linked list, even if it's sorted. And so, you might be thinking like, okay, how can I solve this problem? Well, one of the things that you might think about, and you might be like, hey, this might be a good idea, is, okay, how can I solve the problem of like my linked list not really being good for accessing things in the middle? Because like, if you have something like this, so this is the linked list that we got. Let me erase these, otherwise nothing's connected together. So we got ourselves a linked list, okay? The worst case scenario is trying to access the last thing in the list, right? Because we're searching for something. So you might be thinking like, okay, we got our head pointer. why don't we have a tail pointer that points to the last item of the list? And now I can access that immediately. You know, and that might be useful because if you were trying to insert something at the end of a list, in the scenario here, if you want to insert something at the end of the list, I can't just, I mean, I did sort of slap it in, you know, when I just kind of put it in and you guys didn't question it. But like, you can't just do that. You have to traverse all of the pointers from the head all the way to the end till you get to that null and then replace that. You know, and this will make obvious, these kind of things you'll discover as you're actually trying to code a linked list and you're like, oh, okay, I have to do something like this. So it comes in very useful to have a pointer that points to the last item to quickly shortcut there. And so you might be thinking, okay, can I just do that for the other items in my list? You know, couldn't I maybe have like an index, sort of like that has just a bunch of pointers that basically have like head, first item there, second item there, third item there, and so on. And then just basically access these indices in this sort of array. And the thing is, at that point, you're right. It would just be an array. Because if I'm trying to insert something in the middle here, I've lost the ability to do that in the linked list. Because if I want to put something in between here and then link those together like that, I have to move things around in my table of pointers here, which basically means that I now have a linked list in terms of complexity, and I'm still using an array, which means I still have to move things around. So yes, you're right. Essentially, there is no solution, no matter what you think, of having the advantages of a linked list, but not having the disadvantages of a linked list, I suppose. You know, there's pros and cons. There are better data structures for storing data. There's binary trees. There's hash tables. There's what else would be useful? Well, I mean, hash tables and binary trees are going to be kind of like your ideal solutions depending on what you're trying to do. Because there's like heaps and stuff like that, but those are very special cases. So ultimately, this is not the end of the story. There is more to it, but that more to it is 302 land, not 202 land. So if you're really curious, I have some of the videos on YouTube from spring. I don't have the full class there because we went remote in March, so that's when I started. I started posting in February, but still, you know, don't have everything. But you can go there and check that out, or you can just go on Google and pretty much Google a lot of data structures. But ultimately, for now, you know, we are stuck with a linked list or a array. Okay? And so the tail pointer is useful, and that is actually kind of nice to add because it makes it easier to insert things, and that's actually kind of critical if you want to maintain the most efficient linked list. But that's just a special case. It's useless to have pointers to each individual item of the list because then those pointers have to be kept somewhere, and that somewhere is probably going to be an array, and it's going to be useless, right? Or you can make another linked list of pointers, at which point that's totally even more useless. So, yeah. Okay. What else? The reason I'm not writing anything here in terms of definition is because I have on Canvas a page under the module for linked lists that is called linked list notes, which has all of the definitions and even has a nice picture from the book. Okay? So I think at this time we're about ready to start looking at code. Because right now by the way, this is how 302 goes. You look at a data structure in this conceptual term, and then your assignment is to code it. However, in this class, because we're just getting started, I will basically code it for you, and you will kind of learn from that. But a lot of people I get complaints because they go to 302 and they kind of think that we're gonna do the same system of just like, here, let me code it for you. It's like, no. Once you get to 302, you're expected to be able to make the transition from me telling you an idea and you taking that idea and converting it into actual code. So that's a big jump there. So make sure you're sharp with the coding when before you take 302. Don't slack on the coding. You know, either take 302 immediately, or if you take 218 in between time or something, then code on your own time to keep yourself sharp with code. You want to make sure you're sharp. You're C sharp. It's a joke because there's a language called C sharp. You might not know that actually. But yeah, okay. So ignore the part about templates for now. Again, if this was regular semester, I would be writing this on the board and taking more time. But since it's summer and we have basically 3 days left of class, I'm gonna show you code like this. And yeah, we'll code parts of it, but this is code. Take solace in knowing that at some point this was coded live, I suppose. Okay, so how do we declare, or how do we create a linked list in a computer? We're going to use 2 classes for this. Actually, we only really need 1 class, but ideally you will do 2. One of the classes is going to be to store the node itself, and the other class is going to store the collection of nodes. Okay. Now I put it as a struct here because it made my life easy. So typically they're public anyways. But if you make it private, then you gotta do accessors and getters and stuff like that. So not really worth it. So most of the time you actually will see a node to be either struct or a class, but being public. Okay, and so you have 2 things. Again, we haven't talked about this is technically for a singly linked list. There is something known as a doubly linked list, which we'll get to probably tomorrow. It's going to be just a very minor variation from this. Don't worry about that yet, okay? So singly linked list, which is what we're looking at, has 2 components in the node. And those are the data and the pointer. And the way you declare that is, let's say we're making them of integers. So we got int data, and then the pointer itself is a pointer of the same class. Now this might take a little bit of, to wrap around your head. That we have a struct node, and that struct node has a node pointer inside of it, which basically could point to yourself. Now, if you try to declare code in C++ like class A, and inside of class A you make an object of A, that code will not compile because it'll say it's a incomplete definition or something. Because think about it, it's kind of like Inception, You have an object A, and inside there's an object A. But you haven't finished defining what's in A, therefore, what's going to be inside of the A that's inside of you. And if you look at that, it says there's an A inside of that. But that means that it must have another A inside. So it's kind of like it goes in forever. Kind of like recursion, I suppose. So you can't do that. And because of that, you might intuitively think that you can have a pointer of the same type of the class you're in. That you can have. Because it's just a pointer, and it's not even initialized to anything right now. One way to get code to basically explode is to try to make this point to yourself, because then you have that sort of circular inception thing, okay? But that's okay, we're not doing that. All we're doing is we're saying we have a pointer of the same class that we're making, so potentially a pointer of our own type, but we're not pointing it to anything. Now, I'm surprised I don't have it here. I probably have it beneath or something. But one major quality of life improvement that you can do here is you can initialize next to be null. That will make your life 10 times easier, because if you forget to do that, you will segfault if you try to access a pointer that is pointing to just garbage, right? And also, remember, we typically use null as a way of indicating where the end of the list is. And if you forget that, then you will basically, it's like going on a train and it just, it runs on a track and it just falls down into a cliff. That's going to be you running your code, basically. So yeah. Sorry. Okay. The other thing that could be very useful to have in this class would be a constructor that automatically initializes data to whatever it is. Because it's kind of weird to have, because you think about it this way. With a linked list, you can add objects you can add nodes at any time, and those nodes are objects, so you can add objects at any time. However, there's no point in preemptively adding something if you don't have data for it yet. So it also might be useful to have a constructor where you're forced to initialize data to whatever it is you're creating a node. Okay, so I'm pretty sure you'll see that because I remember very clearly coding that. So it might be beneath it. But anyways, after showing you what a node is, we just talked about templates recently. So here's the template version of that. Pretty much the same thing, except we create a template, class T, and then use T data instead of int data. Okay, and for some reason I decided to call it node type instead of node. Oh, I guess probably because I had it in the same code, so I needed to use a different name. So yeah, same thing. Okay. Now, in this case, in the example, I am going to go ahead and create a linked list without making the second class, which is a linked list class, because you can do that potentially in main. Again, it's not a good idea, but I guess for the first time you're ever recording a linked list, you know, baby steps, I suppose. So we're going to create a head to basically have a way of connecting the linked list, right? To start of the linked list. So we're just going to do node type head. So let's go ahead and create a node and insert it. So the way you do that in code, this is right from the book, is you start out with a dynamic allocation of a node while using the new operator. And again, in this case, I'm just saying new node, but if you're doing it the way that I recommend is you have a constructor there that requires you to already set the data inside of that. Otherwise, look at this. This is like a 4-step process that you can cut down into 3 steps. Because the info part, they call it info, data, same thing as the contents of the value of the node that is actually relevant to us. You could do this by saying new node type and then in the parentheses put 50, okay? But anyways, now you created this node, and also, again, the way that this is done, if you don't set this to null, it's risky. So I would also make sure that you have a constructor that sets it to null, or just put equals null there. But anyways, you have your new node, and this new node is being kept in a temporary pointer called new node. Okay, because you have to have a way of, you have to have something referencing that node. Because if you just make a node in memory and you don't have anything pointing to it, you know, basically if you just type in new node in memory and then that's the end of that. Yes, you allocated a new node, but who knows where it's in memory? You will never be able to access it again. It is gone. Like, I mean, it's there, but it might as well be gone essentially. Okay, and so okay, next, we're going to go ahead and insert it into the linked list. So in this case, we're inserting it like right in the middle of the list, okay? And so first we have to traverse around. So we need to make a temporary pointer, which in this case they call P, which takes us basically to the node before the one we're inserting, okay? So P is just going to start out with head, so P equals head, and then go through each of the nodes and get to the right spot, okay? Once we're in the right spot, then we can go ahead and update the link to the new node. But before we do that, we want to make sure that we don't lose the current spot, because here's what's going to happen. Okay, let me tell you how this can go wrong very fast, very easily. Let's say we got a new node that we're inserting, right? This one right here. And so it turns out that we want to insert that right there, okay? So systematically, this is what you got to do. P gets head. By doing that line of code, we now have a P that is pointing there. If I wish to traverse this list, I can do P equals P link. That is going to make me point from here to there. Okay? So now, because I want to insert my node in there, which I've created by saying temp gets new node 50 or whatever. I naively, what a lot of people I see do the first time they're learning this stuff is they go ahead and say P link gets temp. And this is good in a way because now we went ahead and updated this pointer there. So you inserted it, but you've also run into an issue here. The issue is that how are you going to get this link back? You just overwrote it right here. You just broke that link. So now, good luck trying to link that back in there. Because you lost it. You lost that link. And once you lost that link, it's gone forever. And not just that, you overwrote it. So like, it's really gone. So bad. Yeah. So what you gotta do is first, before you link the node here, you want to copy this pointer first. So go ahead and take plink, which currently contains the pointer here, and copy it into temps link. So basically take temp link, which is currently pointing to null if you initialize it, as I keep telling you to do, and go ahead and assign plink there. That is going to basically do that because it's copying the pointer here. So it's copying this pointer into here. Okay, so basically copying the data of here into here. Okay, so that right now you kind of have sort of like a Y kind of merge, but it's okay because now that you did that, now you can go ahead and do this line of code right here, and that line of code will go ahead and actually make this thing point here. So it's important that you do that process. You first do this pointer here, and then once you've done that, only then do this one. If you do it the other way around, you basically will lose data. You lose pointers, which means that you break the links. You will never be able to recover them ever again. They'll be gone forever, or at least until you run the program again. So that's kind of the important thing to do here, and that's what they're doing here. First, they are making this point to that, and then they're going to go ahead and update this pointer here, okay? Deleting a node here, before I show you that, I think it's easier to do the drawings. Deleting a node is kind of a similar situation where you got to be a little bit careful so you don't break things. So let me go ahead and set up an example here. Okay, so there we go. So we got ourselves, let's say we want to delete this one, okay? That's what we want to get rid of. So first of all, we got to find the node. That's a challenge of its own, actually. We have to traverse this. How do we traverse a linked list? That's quite an important concept that we should know. You should be able to do it recursively and iteratively, by the way. You can basically just go ahead and say, while make a pointer. So let's call it node p, or I like cur. Okay, and assign that to your head. So it has basically what you've just done by doing that line of code. If you just created a pointer that points to the beginning as well. Okay, so now I go ahead and say while cur is not equal to null, which is not. The only time it will be null if the list was empty and the head was null. While cur is not equal to null, go ahead and if you just want to traverse the list and do nothing, you would basically say cur cur gets cur link. That would move you one node ahead, okay? Because cur link is basically this right here, and so that would actually basically copy that into cur, which would have the side effect of basically making cur point to the second thing, okay? So very important to understand this line of code. This line of code is like meta when you're talking about like linked list, okay? Very, very important. Like I'd say the most important, okay? So, of course, you know, say we're trying to delete a specific data item then we could say something like if cur data equals 42, you know, then you can go ahead and delete that. And yes, there is 42 in there. Okay. And so if we are cur data, that means that we are pointing there. Okay. So once we're there, how do we go ahead and delete this? Okay. To delete this, we have to be very careful, because what we have to do is we have to update this pointer to now point there. The way we do that is we need to keep track of that. So let's say that P is pointing there, okay? And be careful, because if you're doing it like I have it here, cur has the same address as that link, but it's not the same variable. So updating cur would not, in this scenario, update the link there, because you could say you've already passed that. So you actually need to keep track of something like a previous pointer, which at the beginning can also just be basically just null. And then down here, before you loop over, go ahead and say previous gets cur, or P, not previous. You'll typically see me use the word prev for previous, but I'm using P this time. So now that we have this pointer like this pointer is technically actually has the data of the purple here, whenever cur has the data of the blue one. That's okay, and it's important because we need to be able to modify the blue circle here. And cur is useless to that, because cur has the same data as the blue circle, but it's not the same pointer. It has just the same address as the pointer. Whereas P has the same address as the purple circle here, which means that we can actually access this pointer by saying plink. So plink is the one that we actually need to modify and update with the next link. So how do we get that? Well, we can say cur link. So that's going to take this link right here and copy it over here, which will essentially do that. However, before you do that, if you do that like that, then you're in trouble, because yes, you have removed the node from the link list, but you've also created a memory leak, because now you have no way of deleting that node. So before you do that, if you're just deleting the node, like if you just want to get rid of it, then it's easy. You can go ahead and delete cur, and then you can just get rid of it. However, that brings up another problem that I see people do all the time. They delete a node, but then they still need the pointer that I was pointing on it. So then they're technically accessing a dangling pointer. So the order of doing things is as follows. Create a temporary pointer of node type. Call it temp. And then, this is in Python, so I actually put the variable type there. Okay. Create a pointer of node type. Okay. And then assign that to basically contain cur. The only purpose of doing this is so that we can delete it later on. We're not going to use this temp anywhere, really. We're just going to keep track of that. Okay, so now go ahead and do your connection, so that, you know, connect this guy here. So you do that with this line of code right here. So you do that connection there. Bam. You took care of that. Now that you did that, you can use your temp pointer and just call delete on temp. Okay? And there you go. Now you have deleted that properly. If you don't do it that way, you're technically either having a memory leak or a dangling pointer. And frankly, both are bad. So this gets a little tricky. Okay? So that's deleting. And so let me show you the example now in the book here. So here we got Oh, I gotta scroll down. It's inserting. We got deleting. We got a pointer already here in the book. They're pointing to, I guess, to the node after what they want to delete. Because I guess what do they want to delete? They want to delete 34. They want to delete 34. So they got the current pointer pointing to 34, which is what they want to delete, and they got the previous pointer. Okay, and so plink is going to point to qlink over there. And then they still got qlink to be able to delete. Qlink will be like their temp pointer, okay? That would be like the temp. They already have the temp over there. So yeah, see, that's not that good of a description. I felt like mine was better than that, but yeah, okay. So anyways, let's look at an implementation of a linked list. Again, we're not doing a class yet. Let's, I kind of just want to code it. No, I'll code it myself next time, because if I code now, we're going to spend a lot of time, just because, I mean, like, when I coded this in class, it took me like the whole hour to code. So if I try coding it now, we only got 20 minutes left for class. So yeah, next time we'll code a double linked list. So first, let's just look at code, and then tomorrow we'll code it ourselves. So in this version, I went ahead and did what I was preaching about the constructor and stuff for the node. So let's kind of look at that for a minute here. I go ahead and well, I don't like this actually. I initialize data to be -1. I think I should have just made a requirement to be passed in as a parameter here. So I disagree with my own code now. But I at least do the null for the pointer. Okay, I am calling the pointer the link next. That's just a personal experience. Like, I use pref, cur, next as my names and variables, and I just stick with them. So that's why you will see in this code next. Nah, yeah. Because I learned that way, so it just kind of stuck. Okay, and so how would you print a node? That's trivial. You just basically get the node's data and the node's pointer, and then just print them out. Again, the whole idea is we are going to, yeah, it makes sense to say consistently. The whole idea is we're going to convert this into a class, because it's a much better way of keeping things than everything just globally, right? That's step 2. And you can kind of take a peek ahead if you want on your own. There's linked list class sample code 2 and 3. Each of these was a different class day. So this was an hour and 15 minutes on this one, and an hour and 15 minutes on this one that we coded in class. So that was the evolution of the code. So you can look at that on your own time, and you can also use that as a help when you're doing the assignment. But like I said, if not tomorrow, we'll code on the live a double linked list, which typically we'll spend about 10 minutes. Some bug we'll find and we'll be crashing, but then we'll fix it. It's good to see that. But yeah, not today. Okay. Printing a linked list is this is what I wrote earlier actually on the iPad. Pretty much the same thing. Cur is not equal to null. Cur is the parameter we're passing in, which will typically be the head of the linked list. But I suppose if you're trying to print from like a certain item on and you already have that pointer, then I guess that's why it's coded like this. Oh, this one's recursive actually. Oh shoot. Yeah, it's recursive, so that's why I probably did that as well in there. That makes sense. Yeah. Yeah. So, wait. What? Why is it recursive, but then we have a while loop? That's just weird. Oh, no. Sorry, not recursive. This is print a node, so it's this function above. Okay. Yeah. Okay. So this is not recursive. Sorry, I saw the word print twice and I just assumed. No, so this is iterative, but print a node is a function that just, like as we said, just prints out like the data and the node next. In fact, if you want to see the sample output, you can go to this link and it'll actually show you the sample output. But it'll just print out the nodes. So this is basically the same thing as saying see out like cur data, which is what I put on my example on the iPad. But yeah,
You know, this is the part where everybody preaches you gotta write comments for your own code. Because I mean, I wrote this probably around November of last year, and then here we are, basically 9 months later. I forgot what the code does. So document your code. Obviously, I'm not gonna document code in the middle of class because I'm trying to teach at the same time. But you know, there you see the actual cases of that. So, and I have not looked at the code since, like, nope, have not. Didn't even look at it today. Maybe I should have looked at it before the class started. Probably do that tomorrow. But yeah, okay. So that is basically the same printing system. Again, cur not equal to null, and then cur next. Again, this is so important. Like, yeah, just keep refreshing. If not, then again, the video will be on YouTube later. So yeah. This is so important to understand. And I think if I try to remember back when I learned linked list, I do recall this being a tricky thing. So you have to think about this as a pointer, and then this is pointing to the next thing, and then you're updating the pointer. Okay, so just stare at this line of code until it makes sense, basically. I'm not sure what else to tell you other than that. Okay? Yeah. I mean, you can ask questions about it if you want, but just make sure that you understand this line of code. It's the most important part of linked lists and pointers in general, okay? And by the way, the reason why it's an arrow here and not a dot is because we're dynamically allocating the nodes using new. If we were not, then there would be a dot, such as the case is here with this. Okay? This recursive one is... This one is actually printing the list recursively. Okay? So, base case is either we are at the beginning of the list, but it's an empty list, or we're at the end of the list and we hit the null. Right? Because if a pointer is null, it's because it's the last link of the list, or because the list was completely empty, so head was null. And so basically, we can take advantage of that as being a sort of a two-edged base case. Then we have the C outing, because we're printing out the linked list. And then the recursion is going to be to pass the pointer to the next item of the list. So let's look at these two. Let's look at because they're basically doing the same thing. One is iterative and one is recursive. Okay? Notice that this line of code is basically the same thing as this. The only difference being that one is recursive and one is not. Again, we're passing in the pointer to the next item. Now, I use head here because it kind of makes sense for the base case, but you can replace the word head with cur if it makes it easier for you to kind of follow that. Okay? That printed linked list, I don't know what this was. We were trying to do things with single pointers. I recall that being a thing. We won't bother about that. We're basically being cheeky with it. Like, yeah. Okay. Is there anything else I want to point out from this? I guess, yeah, this stuff. Notice how many times I have the word next, okay? The reason I was doing this was I wanted to emphasize to everybody that how the whole next thing works, right? What I keep preaching, that you gotta make sure you understand, right? So, I ask you the following. If you see something like C out, head, next, what do you think that is going to print out? What do you think this would print out in a linked list? So that's a question for the audience here. What would head, next do? I'm assuming head is actually the pointer to the head. The second node, or the following data of the next node. Okay, so next is going to print out the address of a pointer, right? Because next is a pointer. Which address would that be? Of which node? So try again. Not quite second node. Because here's the thing. node or head next next. Head would point to the first node. Head next would point to the second node. But head next next is the address stored in the second node's next pointer, which means it's actually holding the address of the third node. See? This is the part where I'm like, it's a little bit trippy. So head next next is the location of the third node. Even though it's kept in the second node's next pointer, it's the location of the third node. Let's maybe draw that out. Okay? So and so on. So head is here. Head data would be the data of the first node. Head next is this guy here, which is in the first node, but it's the address of the second node. Because of that, head next next, this is actually the next here. So this is in the second node. However, it's actually the address of the third node. Okay? Does that make sense? So, because remember, what is stored here is actually the address. It's an address in hexadecimal, which is wherever this guy is stored. But it's in the second node, but it's the address to the third node. Okay? Yeah. Well, we'll see. Well, hopefully you guys are clear now. Oh, we got slashes and random stuff. I thought you were just triggered at this stuff. So, yeah. Okay. And if you want to test it out yourself, you can, again, just click on the link here or copy and paste it into your compiler and play around with it. So that's kind of what I was trying to do and showing. And then I went like crazy. I remember I went crazy because I remember, yeah, I remember this. We just basically spammed next like 50,000 times just to see if it could go. Because what you can do is, this is why you don't want to make this a circularly linked list. If you make a little circle here by like, you know, you link these things together, and then of course the last one should be to null, right? But if you don't make it to null, and you make a point to the beginning over there like that, so you make a circular linked list, and I said head next like 40,000 times, I'm still gonna end up in one of these three, right? And we can by hand try to figure that out. Like for example, I'll abbreviate, but I'll say HN and let's see where that would actually be. So, and let's just say H is here. If that is the case, then this of course is this data here, but it's pointing to the next thing. This is here, then this is here. Oh, I lost track already. This one's here, this one's here, here, and here. So technically this is here, but it's pointing to the next thing. So this would actually give you this node here. Okay. So yeah. So circular linked lists can be pretty nasty stuff to figure out where. So you don't want to do that stuff. But they do have usages with circular queues and things like that. So yeah, I think that's pretty much it for the day. What else is down here? I use Paint, I guess, to show something in class. Here's an example of using a constructor. So this one's, I think, better. Yeah, this one got upgraded. So now we actually have a requirement. Oh no, we were using a default parameter on that one. But yeah, I think that's it. That's all I want to say for that. This is what we'll really do next time. There are two categories of linked list. There's ordered linked list and then there's unordered. We might do an ordered one. an order doubly linked list. We'll do that. That's what we'll spend basically the 2 hours on, because it's going to take us a while to do. And that one we'll code like out of scratch. I'm not even going to look at what I have here, because it'll probably confuse me more if I don't remember it. So pretty confident about it. So yeah, that'll be the plan for tomorrow. And then Wednesday, we will wrap up linked lists if necessary. And if we happen to finish tomorrow, which I doubt, because I mean we spent in class about 2 weeks in linked lists. And so while technically speaking 2 days of class here is 2 weeks of real class, it's not, because there's time you got to process information through. And so like just feeding you all the information in like 4 hours is not the same if it's like 1 hour gaps versus like, you know, blobs of 2 hours. So yeah, I'd rather you guys get this down than talk about stacking queues. So if necessary, Wednesday we will spend also on this. If not, then I'll give you a brief introduction to stacks and queues. Either way, they are going to go over linked lists and stacks and queues in 302. But again, at that level, they expect you to be able to kind of code stuff. So that's why I at least for sure want to make sure that we cover linked lists in detail. So yeah, that's pretty much it. Any questions before we close the lecture? Today's the first day we didn't code, by the way. We coded by hand, but I intentionally made a point of trying to avoid coding in the computer to show you that we're past that stage now, I suppose. Oh, yes, thank you. Yeah. Okay, so now at least there was a good thing about opening the VM, because now I can do that. So I will do that. So while you guys ask for additional questions, I'm gonna go ahead and do that. Compress. Thank you for reminding me, by the way. See, I would have this immediately update on Dropbox, which means I could access it on Windows, but I have my Dropbox full. And I'm trying to set up my own Dropbox server in my house, but I haven't had the time to do it. So are there any other questions? Okay, so now that's put in there. So now I'll go over here, and I'll be posting it under the video lectures. How many program questions are we going to have on the final? You can expect on the final to have something related to programming, at least for templates. Linked lists, you will probably have to do something with that. And then, I mean, I haven't written the final yet, so I'll probably do that within the next 2 days. But basically, the topics that we haven't covered in the first one. So I think it's mostly just virtuals as well. You're gonna expect something with virtuals as well. Yeah. For assignment 11, how would you go about doing reverse display? Well, I show you today with head and tail recursion that you can flip things around. So that's going to be your hint at this, is flip the location of what your print, the cout and the function call for the recursion, flip those. So you're, instead of printing it on the way down, you print it on the way up. That's my hint to you on that. Okay, so I gotta do this. All right, I have now posted on Discord the example so far, and then I'll try to do it again before the final, or at least tomorrow again, I guess. Whatever we do tomorrow, linked list wise, because that'll be useful. But again, there's so much sample linked list code on Canvas that is gonna set you for life, I guess. So anything else? Well, in that case, that is the end of it. I shall go ahead and, like I said, I'll probably try to get the midterm done today. I have to also do the midterm for my other class. So, well, I guess this one is higher priority since you guys are getting it on Thursdays, and the other class gets it on Friday. So, hopefully I get that done today. Cool. All right then. Well, I hope you guys have a good night. You know, get your assignments done, get some rest, and see you guys tomorrow for some crazy linked list coding. So, see you guys. I guess goodbye from the pup. Oh no, she does. She's lying down, so no pup. So, bye.